Okay, so this is where we left last in the last week. We have introduced the method about calculating the areas based on the coordination method. Once you have identified the coordination about all the points on the closed polygon, you can then utilize the coordinates as what you see here based on the x and y coordinates to calculate the area. And with that, you can, with this kind of cross products, y1 times x2 minus x1 times y2, and by summarize all these cross products, you can get the result of the twice of the areas. And always remember that this is two times of the area with the value calculated from the coordinates directly. And then you can get the area of the closed area. And so that's the first method. So this is the one very straightforward method. As long as you are able to find out the coordinates of all the points, it will be very easy for you to calculate the area. And we also, this is only applied for the just a moment. This is only applied for the polygon with a straight line as the boundaries. If we have the situation with the irregular boundaries, as you can see in this, just a moment. What happens here? Okay, if you can see the figure here, the boundaries is not regular, but you still want to find out the areas behind the boundaries, the irregular boundaries, and the traverse line. Then you need to think about a more efficient way. It's not based on the coordinates. You need to find out a more efficient method to calculate the area, and of course, for this situation, the area calculation will not be accurate. It's a kind of approximation about the areas behind the irregular boundary lines. So that's the just a moment. It looks like there will be some issue about my computer. Let me double check this one first. What happens? Okay. That's so weird. Just a moment. What happens here? I will exit sharing the screen first and then reshare it. Now. Okay, it's working now. So we have so for to deal with the irregular boundaries, the first method that we can assume is that we're gonna discretize the boundaries along the traverse line direction into small pieces with fixed intervals, assuming that the interval is the distance is letter d. And then for all the lines, for all the irregular boundaries in the same interval, we assume that there's a straight line. So yeah, originally it could be in a curve, but for the first method, the trapezoidal rule, we assume that it's in a straight line, and then we measure the height of the two boundaries, the two sides, two endpoints of the boundary. say that on the left, for the first interval on the left is h1, on the right is h2. You can also find out the height of all the other points, h3, h4, until you get a hn. And then we can apply the trapezoidal rule to calculate the area of the area covered by this discretized boundaries. For the trapezoidal rule, we can first calculate the area in the under the first interval. This is can consider as the trapezoid, and of course the area here. So that will be half of d times h1 plus h2. And for the area covered by the whole boundaries, you can just quickly summarize the areas of all the trapezoids. So with that, you can get the area under the boundary as half of h1 plus h2 times d plus half of h2 plus h3 times d, and here you get the final interval half of hm minus 1 plus hn times d. So this can be simplified. This can be simplified as the d times h1 plus hn divided by 2 plus h2 plus h3, and here you get to hm minus 1. And this is the trapezoidal rule. You can apply this rule to get the areas directly. And this is for the case where you have totally have m minus 1 intervals. And you have the h1 till hn heights that you can estimate for the boundary lines. So that's the trapezoidal rule. It's one of the approximation about the irregular boundaries. We can always, here let's see one example about how to get the calculated area with the trapezoidal rule. In this example, we assume that there's an irregular boundaries and it's actually in the curved boundary. We want to find out the area between the traverse line and the curved boundary. And we also measure the rectangular offset, which would be the height at the intervals. The interval is set at every 5 meters, and we know the offsets or the heights. So as h1, h2, h3, h4, and h5. So we can then draw this draw the graph to represent the boundary. And we have the traverse line. This is the h1, and this is h2, and we have h3, h4, and h5. And of course, we have the intervals at every 5 meters. So to solve this problem, we get the value d equal to 5 meters. We have h1, h2, h3, h4, and h5. Then we can apply the trapezoidal rule directly. We have a equal to d times h1 plus hn. For this case, that will be h5. That's the last offset or the last height, plus h2 plus h3 and h4. So we have 5 times h1 is 3.2 meters, h5 is 4.4 meters divided by 2 plus h2 is 10.4, h3 is 12.8, and h4 is 9.8. If we do this, apply this equation, do the calculation, eventually you can find out the area is 184 square meters. So that's the way for you to apply the trapezoidal rule to calculate the area of the irregular boundary. So that's the first method. We also have another method as in the trapezoidal rule, we will only use the straight line to represent the curve. But in reality, the straight line cannot show the actual, will omit some part of the irregular curves. For example, if we have the curve and if we have the divide them to the intervals of D, and then for the first interval, usually for the trapezoidal rule, you will use the straight line from D to F, and you measure the areas behind. But here you will observe that there is a part which are missing. That will be this small region which are missing, and this will result in the smaller areas you estimated. So in order to solve this issue, we're going to use another method which is called the Simpson's rule. The Simpson's rule can help us to find out a more accurate estimation of the areas. Usually for the Simpson's rule, we need to consider two intervals at the same time. For example, for the interval 1 and interval 2, and we have the offset or the heights of each point at D, F, and C. And then for the areas covered by this irregular curve, the area based on the Simpson's rule is estimated as D divided by 3 times H1 plus 4 times H2 plus H3. And this is the part, the areas estimated for these two intervals. But if we consider the case with more than two intervals, say that we have n-1 intervals, and here n must be odd, an odd number. And in that sense, if we are measured the height of all the intervals, you can then apply the Simpson's rule to get the area as 1/3 of D times H1 plus Hn plus 2 times H3 plus H5 until you get a Hm-2. So that's for the height with the odd index. And for the height with the even index, that will be H2, 4 times H2, H4, until you get a Hm-1. So this is the way for you to apply the Simpson's rule to calculate the area under irregular boundaries. And also you have to make sure that n is odd in order for you to apply this equation. And if we have even number of the intervals, if n is even, is an even number, then you just apply the Simpson's rule for the first n-1 intervals, where you can apply the Simpson's rule directly, and for the nth interval, use the trapezoidal rule. Then you can get the areas covered by the irregular boundaries more accurately compared with the trapezoidal rule only. So let's go to see the another example, which will be the same example in the first one, but here we want to apply the Simpson's rule to calculate the area behind the boundaries. So we know that there are so we know that there are 4 intervals that we measured, we specified, and we have the height at each interval, And here in this example, n equal to 5. This indicate is an odd number, so we can apply the Simpson's rule directly. So the equation is like a equal to 1/3 of d times h1 plus h5 plus 2 times the summation of all the other height with the odd index. Well, in this case, you only have h3. And then 4 times h2 plus h4. Well, with that, you get the value as 5 divided by 3 times h1 is 3.2, h5 is 4.4, and h3 is 12.8 plus 4 times h2 is 10.4 plus h4 is 9.8. And this will give you the estimation as 190 square meters. This one is actually close to 184 from the trapezoidal rule, but it's larger. So this means that we can actually measure some the part that is not captured by the straight line as the boundaries from the trapezoidal rule. So that's the Simpson's rule. And the next thing I want to introduce is about the actual curve boundaries, which will be in the curve from the circle. If we are provided with the angles, interior angles, and also the radius of the curve, we can calculate the areas accurately. We don't need to apply any approximation about it. For example, if we want to measure the area covered by the lines A, B, C, D, E, F, and the side E to F is in the curve, we can then think about how to estimate the areas of the covered by these boundaries. If for the parts with the straight lines, if we only consider A, B, C, D, E, F with the straight lines, then that will be straightforward. You can apply the coordination method to find out the areas in that region. The only part that we are not quite sure about is how to calculate the area covered by this curve. Once we can find out this value in this rather shaded area, we can then easily find out the total area of covered by these boundaries. So to calculate this one, we need to find out the we can actually use the calculate the area of the curve covered by the curve covered by the EF and the straight line O to F and O to E directly. So the area in this purple shadow would be A equal to I would just say that this one as the circle A equal to pi times r square. So that will be the area of the total circle, but it's just the part of it. And we know that the interior angle is I, so it's just proportional to I divided by 360 degrees. So this is the area covered by the purple area, the purple shaded area. And the next thing we want to find is the it's actually the area of the triangle. So the triangle, so that will be the area of the triangle OEF. And assuming that we measure the length of the straight line E to F as L, we also measured the distance from Q to P to Q as M. Here P is the center line of the center point, the middle point of the line E to F, and Q would be the extension of the line from O to P and intersect with the curve. With that, we can find out the some relationship first. So first of all, we can get the here I will just give you some equations, and we're going to introduce how we derive these equations in the future lectures when we are discussing about the route surveying. So basically, we have the tangent of the quarter of the interior angle I would be m divided by half of L. And also we can find out the relationship R and L, which will be L divided by 2 half L divided by sine half I. So that will be the two equations, two formulas we can derive, and then we can go to check calculate the area of the area of the triangle OEF. So OEF would be, in this case, that would be the EF, the length of EF times the line of O to P, and basically EF is L, and the line O to P. Okay, I'm just try to. The EF is the value of EF is L, which would be the length of the straight line EF, and the OP would equals to R times this should be half of it. This is for the triangle. R times cosine half I, and also should divide it by 2. With that, we can then apply this this equation, this relationship to this equation. We can then simplify this formula as R squared divided by 2 times sine I. And with that, we can find out the red area. The red area. So I just say that EQF as the area of the curve, the area covered by the curve, minus the area of OEF, the triangle, and that would be R squared times pi times I divided by 360 degrees minus half of sine I. So this will give you the areas in the red shaded region. And this is the accurate value of that area. So let's gonna see another example to check how we're gonna calculate the circular area. The chord length, which would be L, is said that the L is 80 meters, and the meter coordinate, that will be M. It's set as 10 meters, and we want to find out the area covered by this circular segment. So first, to solve this problem, we need to first find out the value of I, and also we have to find out the radius of the curve. So to get the value of I, we have tangent a quarter of I equal to 2m divided by L, and that is for this case that will be 2 times 10 divided by 80, which is 0.25. It will give you the angle as 56.145 degrees. So that's the first one. And the second, we need to find out the value of R. R actually equals to L divided half L divided by sine half I. And we know the value of We know the value of L, we know the value of I. This will give you the radius of the curve as 85 meters. And eventually we can find out the area covered by this circular line. So the value is R square times pi times I divided by 360 degree minus sine I divided by 2. You know the value of R, you also get the value of I, which will give you the area as 539.9 square meters. So that's the way for you to get the area. For you to get the area of the under the curve, circular area. So I got questions about the tangent. So are you talking about the which part are you talking about? The are you talking about the so I guess I get the questions from Mark. Can you specify which one are you mentioning? Do you mention this equation or some other?
Yeah, that one. So is it tan I divided by 4?
Yeah, it's a tangent I divided by 4. It's a quarter of the I. I is this one. Just try to mark with red. So this is I. This is the angle. The angle, interior angle of that curve.
Okay, thank you.
We will show you more details about how to do this calculation. This is actually the deflection angle you're going to use to lay out the curve. And there will be more details about how these values are calculated and obtained from this graph. This is we will include them in the route survey for the next week lectures. Okay, so that's the calculation based on the for the circle line, and we also have another simplification, another approximation about the area, which is called the parabolic segment estimation. With that, you can quickly calculate the area covered by the circle line as 2/3 of L times M. And if we refer to the previous example, we have M equal to 10, we have L equal to 80, and then you get the area, approximate area, as 2/3 of 10 times 80, which will give you the result as 533.3. It's quite close to the true value, 539.9. So the if you don't want to apply the complicated calculation, the parabolic segment approximation can also be applied, and you can easily get the result quickly by only knowing the length of the chord and the offset for the from the center line of the curve and from the midpoint of the curve and the midpoint of the chord. So that would be the all the information I would like to share with you about the estimation of the areas. We have 3 different, actually one major method applied to calculate the areas covered by the straight lines, where I can use the coordinates to do the calculation. And for the irregular boundaries, you can use the trapezoidal rule, the Simpson's rule. For the circle boundaries, you can apply the calculate the exact area based on the chord length and the coordinates of the bit of the middle points. And you can also use the parabolic segment rules to find out the approximate value. Okay, so that's the part about the area calculation. Do you have any questions you want to ask? Okay. If no, then I will go to the second part, the lecture about the electrical distance measurement. This would be the part that I want to give you some brief introduction about some electrical tools that we can use for the measurement of the distance, angles, directions, and so on, and also include the horizontal and vertical distance. You have already applied most of the tools in your experiment, but I will give you more insights about how this distance and the angles are measured with these tools. So in your experiment, you actually applied the total station to measure the distance and angles, which will be quite straightforward. You can get the readings from the screen directly and have the record in your field book. That's also the advantage for us to use the electrical distance measurement tools. And for the total station, we can measure the distance, including the horizontal distance and vertical distance, and also the horizontal and vertical angles simultaneously. And with that, you can find out the relative locations or relative distance and directions of 2 points, any 2 points, with one measurement. And in this class, the model gonna use is the Leica total station, and it's easy for you to operate. For the total station, the most important step for you to operate is to do the leveling. Try to do the adjustment to make sure that your equipment is placed it's balanced at different directions, and you have some laser points to pointing to the ground, and also you have some electrical leveling system to tell you whether your adjustment is appropriate or not. I will not go through the details about the adjustment. You have implement all of them in the field experiment. So I believe you are familiar about how to operate these instruments. And regarding to the measurement of the or to the values measured by the total station. Actually, for the total station, only measures two. For one measurement, it only measures two values. One is the direct distance from the instrument to the target, and then it will also measure the vertical angle. For your records, you need to input the height of the instrument, which would be the distance from the ground to the point, to the telescope that you applied for the measurement. And also you have to measure the height of the reflectors, where is the target point. And then based on the distance you measured, the direct distance you measured, which we call the slope distance, and also the vertical angle, you can find out the all the informations, the horizontal distance and vertical distance you need. From the measurement, you have the vertical angle as theta, and if you the system also measures the slope distance as, you can find out the horizontal distance as the horizontal distance capital H as S equal to S times cosine theta. And you can also find out the elevation difference between the telescope of the total station and the target reflector as S times sine theta. So this is the way for you to complete the calculation. The way for you to find out the value of the horizontal and vertical distance in the total station. For the horizontal and vertical. For horizontal distance and elevation difference, they actually comes from the calculation instead of direct measurement. And this is the typical basic information from the total station. And now the questions you may raise is like how the distance is by how the slope distance is measured by this all this kind of the electrical distance measurement system. Usually, for the most of the tools in the market, there will be two different technologies applied for distance measurement. The first one is called the time of the flight. The second one is called the phase measurement. I will go through them one by one. The time of the flight method is very simple. Basically, the electricity measurement system will generate a lot of the short infrared or the laser light pulse, and it will send from the total station, from the total station to the target, and then reflect back. So it has a back and forth, and then based on the velocity of the light through the medium, we can then estimate the distance with the velocity and also the travel time from the start point to the target and back to the total station. And in the actual measurement, we will send a lot of pulse, the light pulse, and then do the calculation for many times. Usually we can send the pulse around 20,000 times per second, and then average everything together. You can get the distance from total station to the target. And this is the way for you to do the calculation. This figure shows the how you're going to calculate it. Basically, you have the target. This is the target. You have the c. C is the velocity of light, and t is the trip duration, which is the duration from your start point to the target and then back to your receiver at the total station. And with one pulse, you can calculate the distance based on the trip duration. That will be c times t divided by 2. And as we say that we're going to do a lot of measurements, we have D1, D2, or we have thousands or tens of the thousands measurement at every second. And then the actual distance measured would be the summation of all this individual distance measured from each pulse. And that will give you the average distance you're going to need to use from the start point to the target. And this is the time of the flight method. But there are some issues about the time of the flight method. You know that the speed of the light is very high. The speed will be around 30 kilometers or 30,000 kilometers per second. So that means that the duration, the trip duration, will be very small. And well, if we have a very small error in the measurement of the trip duration, you might experience the very large errors about the distance. So in order to overcome this problem, we will try to introduce the second method, which is called the phase measurement. And in this method, the machine will send the wavelengths of the light. They send the light with different frequencies of the waves, and in that sense, the wave will reach to the target and reflect back. And by measuring the phase difference from the center of the machine and the receivers of the machine, we can then apply some equations, which I'm going to introduce in the next few slides, to calculate the distance from the machine to the target. So this is the fundamental ideas about it. For example, if we have a wave sent to the target and reflect back, and we know the length of the wave. So here lambda is the length of the wave. And we also know the frequency. we can then calculate the relationship between the wavelength and the speed of the light. So which would be c, the speed of the light. That is c equal to the wavelength times the frequency. The frequency indicates how many waves at every second. For example, in this case, if you have in this figure, you have 4 waves, and you identify there are 4 complete waves from the machine to the reflector, then you can calculate the distance as n times lambda divided by 2. So lambda could be, in this case, lambda would be c divided by f. And if f is 300 kilohertz, then you can know what's the value of lambda. And if you set another frequency, you probably get 5 waves. Still, you can apply this equation, but you will have different values of lambda. So that's the ideas about using the waves to calculate distance. But in reality, the for the ideal case, if we don't have any partial waves length sent, then that would be good. The Mayer distance could be 2 times L. The twice of the Mayer distance will be just n times lambda. Let me just go back to check whether I missed anything. Yes, it's the same thing. So here, so with that, you can get n equal the distance L equal to n times lambda divided by 2, as what I showed in the previous page. N is the number of the complete wavelengths, lambda is the distance of each wave. So this is only for the case you don't have any partial wavelength sent. But in reality, the machine cannot count how many total waves are sent. So we don't know the value of n. So there's no idea for us to know the value of n, the number of the waves, and we cannot guarantee that the transmitted and reflected waves can be mirrored of each other exactly. So there might be some partial waves from the back. So in that sense, this will make the in that sense, we cannot use the equation. We cannot use this equation for the calculation of the distance. But the good things, like the machine is capable of measure the phase difference between the outgoing and incoming waves. We know how much the wave is shifted from when we send it out and when we receive it. So this is called the phase that we can use, and usually we apply the phase meter to measure this phase difference. And with this information, we can then apply some advanced phase measurement tools, technologies to calculate the distance. And I don't think I have enough time to give you the detailed introduction about how to use the phase difference, how to send the multiple waves, the waves with multiple frequencies to find out the accurate distance measurement. I will put that one in the lecture tomorrow. With that, do you have any questions about the lecture today, or any questions about midterm? By the way, we're gonna have the review session tomorrow, and we will show you more details about what we will cover in the midterm and what's the format for the midterm. Okay. Any questions? So get questions. So you are talking about the lab questions. We use the measurement to calculate the horizontal distance. I mean, for the lab, in all your lab experiments, you are using the total station. You don't need to use the you don't need to calculate the horizontal distance by yourself. the machine calculated automatically. That's also the advantages of using the machine. With the machine, you can get the horizontal distance, you can get the vertical distance automatically. You also can get the vertical angle, and the of course the if you do multiple lines, you can get the angles of two lines directly. Okay, do you have any other questions? Well, if no, then that will be all about the lecture today. And thank you very much for your time in the lecture. I will meet you tomorrow about the more details of the meeting exam. Good. Okay, that's great. Thank you very much, and I will see you tomorrow.